I fit somewhere around a fifth grade status with computing. So I'll be very interested to hear what Max has to say. Welcome, please, Dr. Bill Maxwell.
Whoop. Hit the wrong button.
That's a history of computing for you.
That's what I was going to say. Perfect.
Whoops.
Wrong screen.
Coming. Here we go. Okay, finally worked.
Yeah, start the slideshow.
Thanks for inviting me, Kirk. I don't know why I thought this would be a good topic until my memory took me that memory lane. And I'll talk about my involvement with the computers that we had at that time in the period 56 to 65. Some of the pictures and memories are taken from John Rodin's History of Computing at Cornell. He was director emeritus and was there from almost the beginning. He died in 2018. And a lot of the use of computers for administrative work as well as research work and initial machines are located in there. There'll be several agents that some of you may have heard of or know. First was Andrew Schultz, Jr. He was administrative engineering and the engineering dean. Richard Conway, who was my first teacher and thesis advisor and colleague, was in mechanical engineering and was in the start of computer science. Bob Walker in math was very instrumental right at the beginning. A guy named Harry Markowitz, associated with IBM and RAND, and is very critical in terms of the work that I did. He was a Nobel laureate, not in computer related stuff, but theory of portfolio choice. A guy I met at RAND Corporation. And before that, he was IBM and RAND working in the field that we work. And finally, a Dutchman named Erlang at Bell Labs, and he'll come up and then. So here's my recollection of the first decade of computers. It's in the fall semester, 1956. The first course on computers was taught by Richard Conway. He just completed his thesis under Andrew Schultz, the professor, and eventually of the department, eventually dean, in mechanical engineering, which is many of you know or know, the mother lode of engineering at Cornell. And electrical engineering started off in the Franklin, out of ME, and down the line as IE did out of mechanical, and as did computer science out of IE. Fall semester 61, my first teaching at Cornell, the course of digital simulation, taught by me, who just completed his thesis under Conway. It's incestuous at this point, because Conway has also done his work under Schultz. And Andrew Schultz saw the future of computing, at least as far as engineer is concerned. He had worked during the World War in logistics and understood how computers could be used to study logistics. So the first machine that was really controlled a computer was an IBM 650. It was on Phillips Hall, 2,000 locations of 10 digits of data. I mean, that was, to us was enormous, but 2,000 is not even the scale today with amount of memory that you have. It's a drum broken down at the parallel rings of locations rotating at 20,000 RPM. And it's the time from 1 second to the next, so it's that number of milliseconds. And I have down here, oops, bottom of the screen. That's the seconds we have for 734 milliseconds. Compare that to the fastest time we have now. Just a large factor in terms of the speed of access of memory. And in terms of computational speed, it's in billions, okay? And in terms of amount of memory. Input and output was by punch cards, just 80 columns of numeric information. The digits 0 to 1 and two punches, 112, a punch, and 11 punch, over punch, which was the coding of letters. We had external printing. So it had a double length register, used a 10-digit instruction, and I'll go through, it broke it down. You had digits 1 and 2, what to do, and where the data was, and then where the next instruction was, and to branch out, you had branch on the value of the register and where the next instruction is if you're true, and the next instruction are false. So essentially you had computation into a register and the ability to branch, and that allowed you to do testing and iteration. Here's some pictures from the web. Pin-up picture. All these pictures you see here are, white shirt and tie and coats, and that's the way it was. This was the control unit, and this was the punch. There's the magnetic drum. I dare you lift the thing up, right? And the load punch card, in which we punch the numbers of location and then the instruction. All of these in digits and numbers. At first, we had no way of any symbolic way of entering, something into the machine. Here's an early picture of some of the faculty getting. There's Conway and Dick Lesser, who was head of the computer center. John Manis, he was a associate of dean for a long, long time, and Bob Walker in math. So that brought the first course in instructional computing. What happened is they got a grant from big amount off to buy the 650. And the idea was that there would be a 4-credit-hour course in computing taught. It wasn't a course in programming and had to file an outline by IBM. And Conway was the first teacher. He talked with Schultz, and he had just finished his thesis, just gotten his PhD, and he got an assignment to teach the course because he had used the computer in coursework. And the course when it was taught, it was taught, had 45 graduate undergraduate students. I was one of them, and I was in my 5th year of the 5-year mechanical engineer program. I was a top student in a class and top student in mechanical engineering. In the summer of '58, I was at that point now a graduate student. We used the computer to simulate the systems with random behavior. Conway had done that as a thesis to look at a simple waiting line problem, and I had described in a term paper how it could be done to operate like machine centers that found in industry. I had worked at a punch press during the summer one time. I'd done my 5th year project at Chicago Pneumatic Tool, and knew that routing problems and determining what to do next within a machining environment was a critical thing. The idea of simulating a telephone snake go way back to the work of Erlang. And he was in 1929 at Bell Labs. And we all know through statistics, and if you get numbers between 0 and 1 that's sort of uniform 0 and 1, you can use anything in terms of the distribution of values. And the ones he found in telephone were this red one down here, which is called an exponential. A lot of numbers, small values dominated. If you sum them up, you get something that sort of goes like this. And those were his distribution of families. And what he did, he used tables of random numbers in 1929 to draw numbers, decide from his distribution how long the thing was going to go, and simulated how many of the operators on a telephone exchange were busy, when the load had loading, and look into different ways of controlling the computer. Now, this is the flagpole and the drunkard's walk problem. Yep. Nowadays they give it as a course in a problem to people that are programming the first time. If a drunk steps away from the pole and he goes 1/3 forward with probability and 2/3 backward, does he reach 10 feet in 10 moves, for example? And as a drunk, it's not been experienced that this normally can get 10 feet. Normally it falls down after a couple of times. But that had application really in physics. They were trying to find whether a radioactive particle would go through a nuclear shield. And they often was done mathematically through a grid, and they proposed, in fact, by doing it by having a random walk through the grid. You go from one grid point to the next one equally around the four that are surrounding you by a certain free energy, and you meet something there and it goes in a different direction with a maybe change free energy, and you track whether in fact it's gone through a certain thickness of the lattice work that you're simulating on, again using random numbers. So those ideas were not new to us. And so in the summer of '58, we started an experimental investigation of job shop scheduling. Now we squeezed, now I use the word squeeze to pull out letters, because that's actually what we did. We got this program on 2,000 words of data and instructions. We had a coding table dedicated to us in room 50 Upson, big sheets of locations and the content. We had a sheet that says where the data is, and when you operate an instruction, you go pick where the data is to get its address, and wrote out the 10-digit instruction. And we had 9 machines in the job shop and jobs with so many operations at random processing times. And I remember, eventually what you're trying to do in this drum rotating around is, if you're telling it, where do you pick up the data, and you know how long the instruction takes, you know the nearest thing around the drum that you would like to go to. And so, we're trying to minimize the operation of latency on the drum, what it's called. And we got to a point where some locations across the 20 parallel locations that are equal as far as distance from you. And we started to label places around the drum, and you had to pay a penny to get some and a nickel to get other. And there's some places really that you were getting loaded up, and we had a dime pot that you put in with Dick Conway, myself, and Bruce Johnson programming together. And the result of that work was a publication of our results. And we also defined an article in the field of digital simulation. We had an article in the field of digital simulation that laid out the work for many, many, many years, and still people are looking at the things that we're concerned about. I had to mention Dick Conway was a tremendously good writer. He was a fantastic with words, and he usually did all the writing. In fact, he maintains when he took a leave in 1961 that he was glad to get away from editing Maxwell's draft of the thesis. I had been his TA in the course on computing, and in the summer of '60, we realized that what we had to deal with, with even eventually when things were symbolic, so you didn't have to write 10, but you wrote down add, and that was changed into the 10 by a program, for example, that it just was not a good way to teach about language and computing. You really didn't have to write down at that sort of level. So there was languages like Fortran and some offshoots that we tried. It just not right for a first course in computers. And we set out with a grant from Dean Dale Corson to build out an introductory instructional language. It had to have the concepts of computation, conditional execution, that is branch, and iteration, that means go through an array of numbers in an easy way without having to construct conditional execution in the process. What we introduced then was the idea of error correction as well as detecting errors. And in the next version of Cork, which was coupled, we carried that error correction through. And then when I broke off with Conway, when he went to computer science, he continued that work in a language called PLC, and which was used at many, many universities and other places. It was developed for a machine which came in, the Burroughs 220, which had 3,000 words of 10-digit storage. 50% increase in space, and a 1604, which is the first machine that had what was called core memory, which was a guy at Jay Forrester at MIT is the one who developed it. He's known for his thing called industrial dynamics, and he probably could explain what the supply chains are going through now. He was an electrical engineer, and like Ken knows, you take a system operating a little bit and you disturb it with a time lag or something, and things really go haywire. These were located in Rand Hall. Dick and I wrote the compiler together. We had to learn to write compilers. And for a while, the contenders were, Dartmouth was developing a thing about BASIC, and up in Waterloo, they're going with a thing called What For? And we had hopes of challenging them, and it never happened. BASIC came through, and BASIC stayed around for a long, long time. Here's the Burroughs 220. What you find is a raised floor because a bunch of cables underneath. You find air conditioning, the ducts up there, a console, a paper punch as well as a printer. We have the card readers over here and control unit with a raised floor. And next door there was a 1604, which had now a new media, which was external tape systems. And I am glad we are away from external tape systems, because even with labeling, you know, an operator is not being careful, mount one of those, and in a short time, all your data is gone. Or you use last month's data to update instead of the current month, and you go haywire in statistics. So it's you got to be really careful with that. Now, in terms of Cork, the language that we produced, there was a manual, Conway, Maxwell, Walker, and again, very well written. But here's how it worked. You wrote on a coding sheet, it's symbolic, like that, you know, let A equal to B plus C. They were key punched externally by a key puncher. The printing came out, they ripped off the output according to the, you know, a batch run of the cards that were produced by someone else, not by you. And then a big table where you took the original coding sheets, matched them with the output, and gave them back to the students, presumably overnight service. That's the way it was. And that's the way many people during that period, up to 62 or 3, I believe, we were using Quark. Okay. Now, in 61, I introduced a course in digital simulation. Whoops. Yeah. Dick Conway had taken a leave to RAND Corporation. I was teaching a computing course and a course in digital simulation. My workload was Monday, Wednesday, Friday, the computing course, and Tuesday, Thursday with a Saturday lab, the simulation course. And it was for Master of Engineering students, first, 5th year students in the mechanical, and then Master of Engineering students and PhDs. This guy Markowitz had worked at IBM in Hickory Run, simulating a line. And he developed a language for simulation. IBM wouldn't let him publish it, and he moved to RAND Corporation, which in those days, in the 60s, was a hotbed of people working in the field that I was working in, called operations research. And he devised a language for simulation writing called SimScript, using what are called today objects, attributes, sets, and events. And I remember being at a symposium of people that were interested in what he did, and sitting at an evening where people describe their problem in psychology or whatever, you know, plant breeding, or whatever it be. And Markowitz, you know, with his view of this world in terms of Markowitz glasses, would describe how they would describe that problem and what were the objects, what are their attributes, what were sets and you know, and events. And I remember, you know, it didn't take very much. It's not complicated. I had to take the undergraduate math algebra course with a guy named Agnew, which was all about set theory. At the beginning of the course, he says, this is all you have to remember. He says, all Greeks are cooks, but not all cooks are Greek. And then he went into abstract math and algebra. But I still remember that's really all I have to know, you know, when I'm dealing with computers and these notions of sets for computers. None of them have the abstract algebra. In 62, Exxon had a processor for SimScript programs. I had the student type in their SimScript programs on cards. I took the batches of cards in boxes, put them in the back of my VW, and drove down to Exxon to process the student decks of cards. It was a disaster. You know, half of them or maybe more made mistakes. There was no way to correct them, right? And we did correct the problem. I'll leave that. Okay. Then in 65, and actually in 64, we developed the Cornell University programming language. And in terms of execution, as far as the way the student looked at it, none of these coding sheets. You had remote batch and campus and key punches there. So the key punching you could do on a key punch, and it was finally many of them printing key punches so you could see what you key punched, and submitted by batch. And as far as engineering was concerned, it was in the basement of Upson. Yeah. So, and you got your listing the next morning, and that was until 65, until 69, the way computers work. Okay. And here's the IBM 650 computer, which is out at Langmuir Lab. And again, the tape drives. A new thing, which is now we're getting more external disk, which was mountable. The same problems, so you got to get the right disk mounted. But a lot of data could be on this disk compared to what you could get on a tape. And eventually, the tapes and disk went, as we know, became, what we have is your memories probably down in Texas somewhere in terms of if you're using the cloud. So, okay, in 65, that was the beginning of computer science. Dick Conway and Bob Walker, supported by then Dean Andrew Schultz, wrote a proposal to get a grant of $1 million and formed the Department of Computer Science. And those of you that are around knew that grew tremendously. It branched out and started both in engineering and the arts and sciences, and now is overarching in the university as far as computer work on the campus. And, Uriette Manis, Jerry Saltman, Dave Breeze, Bob Constable, and others were hired. Jerry Saltman is interesting. He came from Harvard and brought the Harvard accent. He was interested in information retrieval, and he hoped to see the day when the work he was doing would be able to access information in the Cornell Library. And he never saw that day. He died, unfortunately, early. But many of the students that work for techniques of doing information retrieval and so forth had ideas that made their way into what's commonly used in Google search and other searches. So there you are. What was the way of computing? What was the way of research? What was the way of equipment? What was the way of languages? A short talk, and thanks for joining, and a traipse through what was an exciting period of my life. I just happened to be the right person at the right time and lucked out to have a fantastic career amongst young, bright people at Cornell. I haven't looked at my watch, but I would certainly have time for questions, time for other retrospection or involvement. And that's the end, Kurt.
Max, Jim Persanti here.
Yes.
In 1965, in basic engineering, we were still using Cork.
Yeah, yeah.
Now, the other Cornell language was in existence at that time?
Couple, no, Cork, Dick and I were involved in writing couple. And that's 65 is when it started. So you're right on the cusp, yeah.
Okay. And were there problems with the students and the accuracy of the punch keys, the punch cards?
That I don't remember, yeah. There was probably the beginning for us. We used to patch up holes in the beginning.
You're making me feel better, I'm telling you. Because the turnaround was nowhere near as quick as what you were saying with couple.
It could be, yeah. But I mean, as far as the alternative like Fortran and so forth, we wouldn't have had as many people. My wife took a course under Dick. He introduced in 69 or 70, programming for poets. So, yeah.
I'm wondering how many people dropped their card decks walking across the engineering quad on their way to Upson. Anybody besides me?
Ken, you were punching your own cards? Because we were handing in the that form that Max was showing us earlier. And then we'd come
special
show up
privilege.
later. And it was one of these deals where if you looked in the box where your printout was supposed to be, if you only had a few pages, you did all right. If you had a whole bunch of pages, you had an infinite loop, and they would be pissed off at you.
Yeah, we had no protection of what we call a whirlybird, right? Flies around till it flies up its own, you know what? Every decreasing concentric circles, yeah. Yeah. And, you know, we're still, even with the computer language we have today, you can write a program which will do that. It doesn't take much. But we often write what I call a recursive, a program that calls itself, you know, a routine that calls itself. It's a fantastic way, but you got to get it right. Yeah.
One of the fantastic things that the operators did down in Upson that ran the computing center is they had time on their hands when they were having a good day. So they wrote banner programs. You could make a banner, printed big letters on these continuous sheets of paper. So lots of folks would submit something to go on a banner. Well,
Yep.
my roommate happened to be working there in 1969. And that was when they picked the draft numbers for Vietnam. And his number came up 9. So he turned on the banner program and he burned an entire box of printer paper, printing number 9, number 9, number 9. And he started when he left work that night, sheaving out, carrying the box. It went all the way from Upson into College Town, down Eddy Street, and starting to the beginning of East Buffalo Street where we lived. That was his statement of frustration. So when he got out of school, he joined Hyman Rickover's nuclear program, and the rest was history.
I was an undergraduate student at Johns Hopkins in 1969. And I remember some of my fellow freshmen with these boxes of punch cards and looking at that like, my God, is that that looked incredibly tedious and largely useless. So banners were about the only thing productive I saw. But my
Here's a box of cards listing.
Do not fold, spindle, or mutilate. Well, I have no experience with the Cornell
my
languages.
question,
Oh, yes.
computers in
You're
that
back.
decade.
You dropped out for a while, Kirk, so try again.
I'm sorry. I was wondering what actually useful productivity was allowed by the machines in the decade of the 60s and in the late 60s.
I have no idea, but I know in about the 1963, 64, no one was allowed near the console of the machine, and, you know, and the buttons on the machine itself. Yeah. Yeah.
You all, Max, led
Thank you, muted.
the use of computers with doing simulations. And if I were to ask one question from all you know in operations research and supply chains, and because you did groundbreaking work all your life in that, how would you solve the supply chain problem we have today with all the ships at idle at all the ports? Do you see a way out?
Well, I see the information. I mean, I just read the article today. And my understanding is that they don't have the information, right? of what's where. And they're stacking 5 high. And that's causing problems in terms of access, right? And you could write a simulation of this guy to say it's a mess, right? But typically simulations have been used, for example, in design of airports, okay? Design of luggage handling systems, and I'm not sure if Amazon and theirs, but I'd work with SI Handling in Easton with Jack Bratt in terms of studying the equipment that they were using by simulation. When I went to Rand Corporation in 65 for a leave, the problem they gave me was how we have aircraft would come in after operation with things that have to be done in different shops and by different skill levels. So multiple operations which have to be done, and of course the plane is not done until all the operations are done. And that's the number of planes in the shop is a direct measure of the readiness of the fleet of aircraft, because the complement is the numbers that are operational. And so I study rules of how do you get the stuff, different ways of moving these stuff through the maintenance operation to get the least number of planes on the average in there. One of my followers in our department has been instrumental in studying the rules and the protocol on campus in terms of testing, and all done with simulation work. But the current thing is really a lot of information. I mean, they're just out of space, right? At the this was at the Savannah port, which is the 3rd largest port in the nation. Out of space, and the people not taking stuff, and they know where stuff is. I mean, it's computer tracked, and I'm not sure it's blown up to the level in a stack. It would have to be if you're trying to simulate it and understand it. Yeah.
Right. Did you have something to say, Fran?
Oh, yeah. Well, I was just going to reminisce that my undergraduate was at Pratt Institute in Brooklyn when it had engineering in 1957 to 62. And we had a small IBM machine, and we had to learn to program in machine language, a 10-digit.
Yeah.
And then when I came to Cornell in theoretical applied mechanics, you had thank you very much, we had the punch cards. Seems to me that was a big improvement. And but I remember walking all across to Rand Hall, and then the next morning find out I made a sign error or I punched the cards. Later, when I was working at NASA Lewis, I found that they had a program. This was later. They had a program in the fast Fourier transform, so you can do vibration analysis. And I brought the box. I brought the box back to Cornell, and it was about a foot long of cards just to run the fast Fourier transform. And people were jealous that I had a copy of it, and I still have that box of cards today. So, but I also want to. Some of you may remember we had the Rouleau collection of machines in Upson, and one of the displays that I was able to put on had to do with early computing, and the Sibley School collected a lot of different slide rules. We had a whole bunch of different slide rules, but we also had something called a Thomas arithmeter, and it did 4 functions, all with mechanical processes, kinematics. It did add, multiply, subtract, and divide. And we have one of these machines. Unfortunately, with the redoing of Upson Hall, we're not able to display it, but and this was around 1896 it was patented. So scientists did have the ability to do computation with this four function machine. And it wasn't until 50 years later that we get to the digital machine. The other machine we had when we were running the dynamics laboratory in theoretical mechanics at Cornell. We also had analog computers.
Yeah.
And I tried to save one of those, find one to save, but unfortunately, I could not find any of the departments on campus had saved one. I did manage to save one of the small first Apple computers. So we have a couple saved from that era, but the gap that we're missing is the analog computer, which I like the analog computer. It was more intuitive, of course.
Cut out all those damn card decks.
Better than the card deck, right?
All right, check your garages, guys. Anybody's got an analog computer? Buying.
Don't even know what one looks like. Wouldn't recognize it in the street if I saw it. Yes, okay. Well, so much for all the Cornell reminiscences. I took a computer course in 1965, which started with the theory of a transistor and moved upwards from then and got up to about the troubles of time propagation delays in 16-bit adders. And so we didn't get as far as the machine code because all that convinced me of was that no single person understands everything involved in a computer.
No wonder you changed careers. Thank you, Max.
Thank you, Max.
Thank you.
Let's give Max a hand here.
Thanks, Max.
My pleasure, my pleasure.
And next week, Kirk, remind us.